what I expect you to know is, for example, if I give you these sketches of your molecular orbitals, of the pi molecular orbitals, without aligning the energy levels, can you read them and find out how many nodes are there, and align these molecular orbitals based on their energy, based on their number of nodes? So in this case, what we have at the lowest energy level for that molecular orbital, we have 0 nodes. And then for our phi 2, we have 1 node, which is slightly higher in energy, and that's where your node plane is. On top of it, you have the 2 nodes and 3 nodes. So the more nodes you have, the higher energy your pi molecular orbital will be. So I don't really expect you to know how to sketch these molecular orbitals. They can be more complicated, but you're expected to know the more nodes there are in that molecular orbital, the higher the energy is, right? So count the number of nodes and rank the sketches of the molecular orbitals based on their energy. Once we know the energy levels of these molecular orbitals, we can put electrons into these molecular orbitals. So how many pi electrons do we have? So that goes back to our energy diagram. We know that each carbon have a singly occupied p atomic orbitals. Consequently, in the 1,3 butadiene, we have 4 carbon. That gives us 4 p electrons in these molecular orbitals, right? We start from 4 p atomic orbitals. We end up with 4 pi correlation molecular orbitals. And in total, we have 4 electrons in there. And to put the electrons into my MO, we're following the same rule. We go from the lowest energy MO and goes up. And looking at these molecular orbitals, what we have, phi 2 and phi 3 are our special case. So phi 2, that's our HOMO. Or what HOMO means, that's highest occupied molecular orbital. And then our phi 3 is another special case. That's our LUMO. Or in a different word, that's the lowest unoccupied molecular orbital. Right, so in this case, for example, the kind of question I could ask you is just giving you these random molecular orbitals without telling you which one is lower in energy. First, rank these molecular orbitals based on the number of nodes there are. Second, assign electrons into your molecular orbitals and try to get chemical information out of it. The type of chemical information you can get is, for example, is it diamagnetic? Is it paramagnetic? Are all my electrons paired? That's one part of the chemical information. The other possibility of the chemical information is, can you derive information about the bond length or bond strength looking at your pi-MO diagram? So for example, if we're focusing on the HOMO here, this is the highest energy occupied molecular orbital. And we can derive information about the bond length. So if we look at here, there is a node in between C2 and C3 carbon. Between C1, C2, and C3, C4, there's no nodes. So when you draw the 1,3-butadiene out, we're expecting the pi bond between C1 and C2 and between C3 and C4 being stronger comparing to the pi bond between C2 and C3, because here we have a node. All right. And that's why we actually draw our 1,3-butadiene in this alternating fashion. But in fact, the center sigma bond is still shorter comparing to your normal carbon-carbon single bond. All right. So that's the 1,3-butadiene example. We can have other examples, and you'll hear the term aromaticity. I won't give you a spoiler alert, but we're using the same type of an analysis in understanding the pi bond in other complicated organic molecules. For example, if we're talking about benzene and cyclobutadiene, so benzene has a structure like this. It's a 6-member ring. Each carbon is sp2 hybridized and has a molecular formula of C6H6. On the right-hand side, you can have cyclobutadiene, which has a molecular formula of C4H4. So in both cases, we're having the similar type of the conjugated single bond and double bonds. And we can use MO theory to understand the chemical bonds in these two molecules and try to rationalize why benzene is a very stable molecule, while the cyclobutadiene is a highly reactive organic molecule. It's not stable at all. So the take-home message before we move on is in benzene, we have 6 pi electrons, and in cyclobutadiene, we have 4 pi electrons. You can do that same type of analysis and figure out in both of the molecules, your carbon is sp2 hybridized, has 1 singly occupied p atomic orbitals. And then by drawing out that MO correlation diagram, for benzene, these are the MO correlation diagram we can have. Again, what I expect you to know is, say, right now, if I give you all these MO correlation diagrams, can you tell me which one of them is lowest in energy and which one of them is highest in energy, given the number of nodes there are? Right, so a quick thing we have is in the bottom. This one has 0 nodes. So that's the lowest energy pi MO. In the middle, we can have 1 node. That's where this node plan is. Or we can have 2 nodes. And on the top, we have 3 nodes. Right, so the way we identify the node comes from the position your molecular orbital changes its sign. So in this case, what we have is we observe the orbitals is switching sign when it passes these plan. So this plan is called a node plan because whenever your MO wave function passes that node plan, it changes sign. It can also be through atom. So this is another possibility, right? So whenever you pass it through the node plan, your orbital changes sign. So that's the definition of a node. So with that in hand, we can end up in aligning the energy level diagrams for the pi MOs of benzene. Right, so we start from random molecular orbital drawing, and then looking at the number of nodes in each drawing, you can arrange these molecular orbitals based on their energy levels. Right, the more nodes you have, the higher the energy that MO is expected to be. Next step, we can assign electrons into these MOs. We have 6 pi electrons. We have 1, 2, these are degenerate, 3, 4, 5, 6. So all my electrons in benzene are paired. And it's dimagnetic. And these 2 are my HOMO. These 2 are my LUMO. It's a stable molecule because we have, well, for 1, all electrons are paired. And for 2, these are relatively, we only have 1 node in these HOMO, so it's a relatively low energy pi MOs here. So that's the benzene. We'll use the cyclobutadiene as another example and see how they differentiate from each other. So in cyclobutadiene, these are the pi MOs you can imagine to draw. Again, on the bottom, this one is 0 nodes. Right, all atomic orbitals are shaded in the same way. In the middle, we can have 1 node, either through bond or through atoms. And on the top, we have 2 nodes. So we start from 4 p atomic orbitals. We end up with 4 pi molecular orbitals. And now we can put the 4 pi electrons into the pi correlation diagram of cyclobutadiene. What we have is 1, 2, 3, 4. Right, so these two orbitals are degenerated. So we need to have these atomic orbitals singly occupied to avoid electron pairing energy. So apparently, we have two unpaired electrons, and that's paramagnetic. So that's why the cyclobutadiene doesn't really exist, because these are just diradicals. They have two unpaired electrons. They're super reactive, chemically speaking. All right. Do we have any questions before we move on? Yes. Well, you count the number. So the question is, how do you determine how many degenerate orbitals are there? So the quick answer here, it can get more complicated, but for our course, quick answer is you count the number of nodes. If they have the same number of nodes, we expect them to have same level, same energy level. So in this case, for the cyclobutadiene, these two molecular orbitals both have one node, so they have degenerated energy. On the benzene example, similarly, here we have both molecular orbital having one node, they're degenerating energy. Here, both molecular orbitals have two nodes, they're degenerating energy. So you count the number of nodes. That gives you information about the energy levels. All right. So that's the end for our quantum bonding theory. I'm a little bit behind, but we finished talking about the classical and quantum mechanics bonding theory. So we now have a good understanding on what are the models we can use to describe a chemical bond. Right, so we start by talking about what is an atom. Now we finish talking about what is a chemical bond. And then we want to move on to some of the more chemistry topics, which is chemical reactions. So I'm really ambitious today, so I want to finish all 4 topics. We'll start by talking about molecular formula and mass. Second question, how do you write balanced chemical equations? The third topic will be talking about solution, concentration. At the end, we have stoichiometry or mass relationship. I'll try to finish everything, but if I don't, I'll just pick up next lecture. And next lecture, we'll be doing some comprehensive stoichiometry problems together. So get prepared with a pen and paper. All right, first topic here, molecular formula. So this part is quite straightforward. We have several different formulas we can use. The easiest one is called the empirical formula, which just tells you about the relative numbers of atoms of each kind. So using an example here, empirical formulas are just the simplistic formula of a substrate. So for example, we'll use the formaldehyde here, right? So that's the molecular formula. It tells you connectivity of your carbon and oxygen and hydrogen and so on. But in the empirical formula, what we have is just CH2O. Or what it tells you is the ratio between different elements in this molecule is 1 to 2 to 1. So it doesn't really tell you too much about the chemistry. It just tells you the elements in that specific molecule. With the empirical formula, you can do some calculation that's related to the empirical formula, related to the percentage of the element in that molecule. So I leave a practice problem here. This one should be relatively straightforward. It's calculating the percentage composition from the empirical formula. So let's just say you have the empirical formula to be NaClO. Can you calculate the percentage chlorine in mole and in percentage mass? I'll skip doing the calculation here, but if we're talking about the percentage chlorine by mole, you're pretty much just counting how many atoms are there in that molecule and what's the percentage of chlorine, which in this case, that's just 1/3, right? We have a total of 3 different elements in that molecule in 1:1:1 ratio. So the percentage chlorine in mole is naturally 1/3. If we're calculating that by mass, It's slightly more complicated, but not too much. So again, we know these elements are 1 to 1 to 1. So what we're doing is just counting the number of mass of chlorine over the mass of this entire molecule, and times 100% at the end. But we need to time 100% on the top as well. Right, and in order to do that calculation, what we have for the mass of chlorine, you just read the periodic table, that's 35.5. And on the bottom, that's for sodium, that's 23 plus 35.5 plus oxygen, which is 16 times 100%. So those are the information you can imagine to get from just looking at the empirical formula. And then we can have molecular formula. So molecular formula tells you a little bit more information. It tells you the actual number of atoms of each element in one molecule. So we talked about benzene before, right? So C6H6 just tells you that benzene molecule contains 6 carbon atoms and 6 hydrogen atoms. So what's the difference between the molecular formula and empirical formula? Just a quick question here. What's the empirical formula of benzene, if you think about it? Yes. Yes, so just CH, right? So the carbon and hydrogen is in 1-to-1 ratio. So that's the difference between molecular formula and empirical formula. Empirical formula tells you about the ratio of different elements in that molecule, where molecular formula tells you the actual number of atoms in your molecule. Now, with the molecular formula, we have a bit more example questions we can do together. Well, you see hemoglobin as an example. That's a protein that carries oxygen in our blood. So let's imagine the molecular formula of hemoglobin is like carbon 2952, hydrogen 4464, and blah, blah, blah. Don't want to read that out. Some of the typical questions I would expect you to know is how to calculate molecular weight from that molecular formula. This part should be straightforward. You're just looking for the molecular, the atomic weight of different elements, of different atoms, and do that calculation. How to write the empirical formula. For that, you want to find a common divisor. So in this case, our common divisor is 4. So the empirical formula of hemoglobin, that's about C738, H1116, and 12, oxygen 203, S2, Fe. I cheated a little bit, but you can use your calculator to check if my calculation is correct. All right, so it's just, can you translate between molecular formula to empirical formula? You can't do it vice versa, though. And at the same time, you could be asked to calculate the percentage mole and percentage weight of different elements in the hemoglobin. That's the same type of example we did before. So these are just plugging numbers. It's not hard. So you can just practice yourself and compare that with our annotated notes. This part is relatively straightforward, so I rushed it a little bit through. So are we doing okay before we move on, talking about chemical reactions? Okay. Chemical reactions. So this is probably the most this is one of the techniques you need. It looks complicated, but in hard, it's actually pretty easy. So when writing the balanced chemical equations, there are several requirements you need to fulfill. The first one is you want to make sure the matters are conserved when you're writing the chemical reactions. Like we can't just create atoms from void. We can't just create electrons from void. It's the same idea. We were talking about molecular orbitals from atomic orbitals. We don't create orbitals. We don't create atoms or elements from void. Whatever you start with, whatever you end up with, the mass is always conserved in a chemical reaction. It's relatively easy to write a simple chemical reaction. You can just look at this reaction and say, hey, we start from a methane. It's burning in oxygen. We're getting CO2 and H2O. And we don't have enough oxygen here. We need a 2 and 2 in between. Right, on the left-hand side, that's our reactant. And on the right-hand side, that's our product. And you count the number of atoms in your reactant and the number of atoms in your product. We start from 1 carbon, we end up with 1 carbon. We start from 4 oxygen, we end up with 4 oxygen. And we start from 4 hydrogen, we end up with 4 hydrogen. So the number of atoms needs to be balanced on your reactant side and your product side of your chemical reaction. But it can easily get more complicated. For example, we can have this chromium decompose to form nitrogen gas, chromium oxide, and water. So this becomes less intuitive in how to quickly write out a balanced chemical reaction, how to balance this process. So we have a procedure, we can do it. But if you have other procedures that work for you, you can feel free to use your procedure. I only ask for balanced chemical reactions at the end. So this is the procedure I typically use to balance a chemical reaction. We'll use that chromium complex decomposition reaction as an example. What we have, first step, you put a 1 in front of the compound with the most number of type of elements. So we're looking for a complex that's most complicated, if you like. And we put a 1 in front of it. And we're just putting letters A, B, and C in front of other compounds. So far, so good. Next step, building up that matrix that helps us to solve for A, B, and C. What we have is write out the number of atoms of each element. So let me just put that down a little bit. Right, we're just counting the number of atoms of each element. So in my reactant, we have a total of 2 nitrogen. We have 2 chromium. We have 8 hydrogen. And we have 7 oxygen. Right, so this is just counting how many atoms are there in my reactant. And then we can do the same for my product. How many nitrogen are there? That's A. Chromium, that's 2A, I'm sorry. And hydrogen, that's 2C. And oxygen is a bit more complicated. That's 3B plus C. All right, so what we're doing here in green, we're writing the number of atoms in my reactant. In blue, we're writing the number of atoms in my product. And then we're going to solve for that coefficient A, B, and C. What we have here, by solving this first equation, A equals to 1, that's quite intuitive. Second one, B equals to 1, C equals to 4. And then we can use our last equation as a sanity check and see if we have that correct. Here, 3B plus C, that's 3 plus 4. 3B plus C equals to 3 plus 4 equals to 7. And that's equal to 7, so we're happy here. So, right, what we're doing here is set up this matrix and help us to solve the coefficient A, B, and C. So now we know A equals to 1, B equals to 1, C equals to 4, and that's 1. So we end up writing our balanced chemical reaction, which is 1, 1, 1, 4. You don't need to write that 1 out, though, so we can just delete it. So that's our balanced chemical reaction. I'll just leave that here and do some example together. All right, so this is the example we just did, and using the same procedure, let's do another example of a combustion reaction. So now we're talking about a linear butane burning in oxygen, forming CO2 and H2O. And I might ask you to write a balanced chemical reaction for this new burning equation. So let's do that together, right? So the first one is writing out 1, A, B, and C. I'm just assigning these coefficients into my reactant and product. In my reactant, the elements we have is C, H, and O. I only have 3 different elements here. In my reactant, we have a total of 4 carbon. We have 10 hydrogen, and we have 2A oxygen. In the product, let's do the same. For carbon, that's B. For hydrogen, that's 2B plus, wait, that's just 2C, sorry. For oxygen, we have 2B plus C. And what we're doing is using these equations to solve for my coefficient. Because the atom number needs to be balanced, so we have these equations, and we can solve B equals to 4, C equals to 5, and A is a little bit more complicated. 2B, that's 8, plus 5 over 2, that's 13 over 2. And normally we don't have fractions in our chemical equations, so we times everything by 2. So that gives me 8, 10, and 13. So putting those coefficients into our original reaction, what we have is we have 2, A equals to 13, 8, and 10. All right. Do you have the same number there? Okay. We'll do another example together, which is reaction of sodium hydroxide with aluminum oxide and HF. This gets even more complicated, but the logic is the same. We're just building up our calculation and trying to balance the reactant side and the product side to make sure our atoms are conserved. So in this case, this one is the one that's more complicated with the most number of elements. So we manually set that to be 1. And then we have A, B, C, and D. And likewise, we're just solving how many atoms are there in my reactant and products. So in the reactant, we have A, sodium. We have 2B, aluminum. We have C, fluorine. Oxygen, that's A plus 3B. A plus 3B. Hydrogen, that's A plus C. All right, so what we're doing here is just counting the number of atoms in my reactant. And then we can do the same, counting the atoms in my product. For sodium in my product, we have 3. Aluminum equals to 1. Fluorine equals to 6. And oxygen, that's D. And hydrogen, that's 2D. All right, so now we have this matrix of equations we can solve for. And looking at it, some of them are intuitive. We have A equals to 3, B equals to 1/2, C equals to 6, D equals to A plus 3B, so 3 plus 2 over 3 equals to 2 over 9. We'll use hydrogen, which is a leftover, as our sanity check. So A plus C, that's 9. 2D, that's also 9. So A plus C equals to 2D, and 9 equals to 9. And we're happy. We just use that as our sanity check. And now putting these coefficients into my original equation, we have A equals to 3, B equals to 1/2, C equals to 6, that's 1, and D equals to 9/2. And again, we don't want fraction in our chemical reactions. We time all the coefficient by 2. We end up with 6, 1, 12, 2, and 9. All right. So this is one of the techniques you are definitely expected to know. Write a balanced chemical equation. You can for sure know there is a question related to writing a balanced chemical reaction. Okay, questions so far? All right, next up. Then solutions and concentrations. Solutions and concentrations are things we use in chemical reactions. You will hear people talking about a solution of certain molarity, certain concentration. So before looking into actual problems, what are the definition of a solution? So when we're talking about a solution, what we say is a homogeneous system, right? For example, in here, we end up with a homogeneous system that contains one or more substance. What that means is, say we have solute in solvent. So let's use NaCl and water as an example. When you're dissolving NaCl in water, what you're getting is a solution of your NaCl that's evenly distributed in your solvent, right? So that evenly distributed, or the homogeneous nature, is important when we're saying something is in a solution. One of the common things one of the misunderstandings we should avoid is, say, if in that mixture you have some NaCl solid at the bottom of your beaker, that's no longer a solution because your solute is not evenly distributed in your entire system. So when we're talking about the composition of solutions, we have several units we normally use to describe a solution concentration. So those units, including percentage mass, mole fraction, molarity, and molality, they have different applications. So that's why people use it in different setups. But it's important to know what kind of concentration people are asking for. So we'll quickly go over the definition of these units for concentration of solutions. First thing, percentage mass. So this one is almost intuitive. We're talking about what's the percentage mass of your solute in the entire solution, right? So in this case, percentage mass is defined. On the top, we have the mass of the solute. On the bottom, we have the mass of the solution. That times 100%. Which percentage mass, that's by definition. Or instead of using mass, you could also use the number of mole, which is mole fraction. So mole fraction, it's given by this big X, or sometimes people use a more curvy form of that X. Mole fraction is defined by, say, a solute in a solution is the number of mole of the solute divided by the total number of mole of the solution. And to calculate the total number of mole of the solution, you need to take the number of mole of the solute to plus the number of mole of the solvent. So it's pretty intuitive, like what we did, right? It's just replacing that mass with a number of moles. In chemistry, we use molarity a lot, which is number 3 here. That's defined by the number of moles of the solute per liter of the solution. Or molarity here has a unit of mole per liter. On the top, we have the number of mole of the solute. And on the bottom, we have the volume of the solution in liter. We could also abbreviate the mole per liter into molar, or big M occasionally. And at the very end, in analytical chemistry, we could also use the number of mole of the solute per kilogram of the solvent. So that's the molality. So molarity is talking about the volume of the solvent. Molality is Molarity talks about number of mole of the solute in the volume of the solution. Molality talks about the number of mole of the solute per kilogram of your solvent. So we use molality in analytical chemistry a lot. All right, so this one is a common misunderstanding. Molality is number of solute per kilogram mass of the solvent. All right, question? Yes. Okay, so I mean, these are just the 4 definitions of the unit we use when we're talking about solution. For this class, I don't want you to remember it, but eventually you'll need to remember them somehow in your future classes. People have different definition of concentration of a solution. And when we're talking about solution, we could also have multiple solutes in the same solution. You can have different types of salts dissolved in the same cup of water, right? You can have salt and sugar dissolved in the same cup of water as well. So in this case, depending on what kind of solute you have, your solute might have different concentration. One of the example questions I can have is, say, let's imagine you have 100 milliliter of some type of aqueous solution. When we say aqueous solution, we're just saying the solvent we're using is water. And then in this aqueous solution, I'm giving you the molarity of your 2 different solutes. It can be calcium chloride with the molarity of 0.5 mole per liter, or potassium chloride with the molarity concentration to be 1.00 mole per liter. Can you calculate the molar concentration of the chlorine element in that aqueous solution? Right, so what we have here is the concentration of the chlorine element equals to, we have 2 in calcium chloride, so 2 times the concentration of calcium chloride plus 1 times the concentration of KCl. Right, so the same calculation, we have 2 times 0.5 plus 1 gives you 2.00 mole per liter. All right. Okay. And the last item of my ambitious plan is stoichiometry, mass relationship. We'll go over the introduction, and then we'll do problems together in next lecture. When we're saying stoichiometry, what we're talking about is a mass relationship in a specific chemical reaction. So using this equation of burning hydrogen in oxygen as an example, we're forming water. We have different ways to describe that reaction. So when we talk about chemistry, it's more or less a new language. How do you say this equation to your colleague, to your classmates? We can describe this equation using number of moles. For example, we can say 2 molecules of H2 and 1 molecule of oxygen react to form 2 molecules of H2O in this balanced reaction. That's by the number of molecules. Alternatively, we could also define or discuss our reaction using number of moles. Let me just copy it down again. That's the same idea of saying, hey, now we have 2 moles of H2 and 1 mole of oxygen react to form 2 more of H2O. So these two are pretty much similar to each other, right? Mole is just conversion of one molecule by the Avogadro number to give you number of moles, which is more macroscopic. Stoichiometry, on the other hand, is trying to use the number of mass or the mass on both ends of your chemical reaction to describe this reaction. So assuming 1 mole of oxygen is being used, that's the equation we're talking about, we can calculate the mass of your reactant and the mass of your product. These are pretty intuitive. Here, the 2.0, that's the molecular weight of hydrogen, H2. 32 is the molecular weight of oxygen. And 18 is the molecular weight of H2O. So using the mass relationship, we can similarly read out this chemical reaction here by saying, hey, we have 4 grams of H2 and 32 grams of oxygen react to form 36 grams of H2O. And in reading it out like this, you might want to just check the number of mass here. So the total mass is always conserved in a chemical reaction. I have some examples together. I don't have time to finish. But before I conclude for today, I want to introduce the concept of chemical yield. And we'll pick up these examples next lecture. So before we conclude for today, the 2 concepts I want to talk about are the limiting reagent and the yield of a reaction. When we're talking about the limiting reagent, that's by definition, it is all used up in a reaction. Or in more scientific way, the definition of a limiting reagent is a reactant that gives the smallest amount of the product. All right, so we're talking about a reactant that gives you the smallest amount of the product, which means that reactant is used all up in a chemical reaction. So that's called a limiting reagent. So that's the first thing. The second concept is called the yield of a reaction. So we can have theoretical yield, which means like what we did with that hydrogen-oxygen example, right? You read out that chemical reaction on paper, and you find out what's the theoretical yield. Assuming all my reactants are conversed to my products, how much product do I expect to get? So that's my theoretical yield. At the same time, we're chemists. We work in the 3-dimensional world. When you go into the lab and you do the reaction, you can get the actual measurement of the product that's being formed. So that's experimental observed yield. So when chemists reporting something called a percentage yield, what we're getting is a ratio between the actual yield over the theoretical yield times 100%. Which basically tells you, all right, so that's what we calculated to get, and that's what we actually get. Here's the ratio, which is called the yield of the chemical reaction. I have a lot of examples I want to work you with, but I'll see you next Wednesday. And you feel free to practice that on yourself as well.